Today I'd like to look at a proof for the formula of the derivative of a composite function like this, f of g of x. And an example of this would be sine of x squared, where we have the function x squared and another function applied to that sine x. So one way we can prove this is to use the limit definition for a derivative. And so, like usual, we're going to rewrite this expression in terms of what we're trying to differentiate. So the limit as h approaches 0, and instead of just a function f that we're trying to differentiate, we're trying to differentiate a composite function, f of g of x. So we're doing f of g of x plus h, that nudge that we're applying to this term here, that is approaching 0, minus f of g of x without that nudge, all over h. Now there are two creative steps in terms of simplifying this down into the formula that you might have learned already, and they're not very obvious. They're hard to think of on your own, but when you see them and how they work, hopefully it'll make sense why they're useful for us. So here's the first one. We're going to multiply the numerator and the denominator by g of x plus h minus g of x. And I would never think of this on my own, I don't think, but it works really nicely. So the next part is we're going to swap these two denominators. We can do that because we're just multiplying here. The fact that they're in fractions doesn't matter, but the order of multiplication, we can swap it around and it doesn't change it. That's one thing I'm going to do. The other is, instead of just taking the limit of the whole thing, I'll take the limit of the two fractions separately. So the limit as h approaches 0 of f of g of x plus h minus f of g of x over this part, I'm going to write here, g of x plus h minus g of x times the limit as h approaches 0 of g of x plus h minus g of x over h. Take a look at this part here. The limit as h approaches 0 of g of x plus h minus g of x over h. Hopefully that looks familiar, because that's just our definition for a derivative. And this is with the function g. So this is really just g prime of x. So that's nice. Now all we have to worry about is this fraction. And here's where the second creative step comes in, because we're going to introduce a new variable, and we're going to get rid of all the h's and rewrite the expression in terms of that new variable. So let's call this new variable, let's call it c, and we'll let c equal the denominator here. g of x plus h minus g of x. Okay, so we can get rid of the h here in the denominator because we can just throw in c if we define c to equal this denominator section. We also have an h here though, and so if we're trying to get rid of this h, we need to figure out what g of x plus h is equal to. So to get g of x plus h, let's add g of x to both sides. We'll get g of x plus h equals c plus g of x. Awesome. Now we can substitute this in for here, and we can get rid of the h and get it in terms of this new variable c. The last thing is we're taking the limit as h approaches 0, but if c is defined in terms of h, because there's an h in here, we have to ask ourselves the question, what happens to c as h approaches 0? Is it okay with just swapping the c and the h here when we're doing this limit or not? So let's try it. If we plug in a value of h, we could just plug in 0 really. There's nothing wrong with that. We'll get g of x plus 0, or g of 0, or g of x minus g of x, which will just give us 0. So as h approaches 0, as this gets closer and closer to 0, we'll get closer and closer to g of x minus g of x, which is 0. All that is to say, we can swap the limit as h approaches 0 just with the limit as c approaches 0, because as h approaches 0, c will approach 0 as well. Let's get rid of all of these and write the new ones. So this is f of c plus g of x, and I'm going to write g of x plus c, minus f of g of x all over c. This is what it looks like now. So hopefully this also looks familiar, because this is another limit expression that looks kind of like our limit definition for a derivative. It's a little different, but notice how if, for example, we cover up these g of x's here, it's our f of something plus c, and that c is approaching 0. In our limit expression, it's f of x plus h, where the h is approaching 0. And then here, it's without that c. Here it's without that h. So it does look the same. The difference is our input here is the function g of x, whereas in the definition, it's just a regular x. So instead of calling this f prime of x, we're going to write f prime of what is the input into this limit expression, g of x. And that is what this expression is referring to, the derivative of f of g of x. And we still have times this, and there's the formula.